be okay. So we're going to be talking about some homework problems. I've got lots of people signed up for chats, so that maybe we could talk about it all together here in a video. Okay, so the first problem is to try to see about the variance of the data projected to a standard basis vector, and that should be the usual variance for the data, right? And so the idea is that if you have a bunch of data points, x1 through xp, right? And these are in Rn. Projection to EI would result in EI, well, you could put x first if you want, transpose times x1, dot, 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 EI transpose xp. And so the thing to notice about this data set is that these are scalars, right? And so you have p scalars, and so you can form the variance for those. So to then take the variance, and so what is the variance for a set of data like that? K equals 1 to p EI transpose xk squared. Okay, but of course, what is this? Oh, by the way, I'm assuming here that the data has been mean subtracted, and that's fine if you want to do that. That'll make the, if you don't, then you have to mean subtract at this point, right? Okay, so then just think about what this is. What happens when you dot the vector xk with the basis vector? What do you get? Okay, so that's number one. Number two, we have the same set of data. But what are we doing in this case? Let me double check to make sure I'm going to say the right thing here. Suppose I have two orthonormal vectors u and v in Rn. Orthonormal. Given our p points, compute the covariance between the data and show that the result is u transpose CV. Okay, so if I'm going to be computing the, or if, first off, I need to project the data. So I have data set 1 would be u transpose times x1, u transpose times x2. This is why it's important to have the normalized vectors, right, for our projection. Also, I will assume mean subtracted again, just to make that easier. Data set 2 would be the same thing, v transpose x1, v transpose xp. Okay, and now I have a set of scalars here that I need to compute the variance for. And again, mean subtracted. Good. Now, how am I going to compute the covariance between these two? That's 1 over p minus 1 times the sum, k equals 1 to p, of u transpose x k times v transpose x k. Right, these are two scalars, right? So that's taking the place of the square. Now we want to show it's the same thing as that, right? So it might help down at the bottom here to maybe write down what is u transpose c times v. If I rewrite that, that's I can rewrite this as 1 over p minus 1 times, remember, x1 transpose plus xp transpose times v. And so is it possible to get from here to here? How would we do that? Here's a hint. The dot product, you can switch the order. And so in place of v transpose k, maybe we'll write xk transpose times v. Okay. Now you're just one very, very, very short step away from completing this completing this thing. What is this? Okay. All right, so that's number 2. Now we're going to switch gears in 3 through 7, and we're going to be doing computer programs. So just as a hint here, I think these are probably a lot easier to do in MATLAB than they are in Python, but if you have a lot of experience in Python, then probably stick to that. So number 3, where is it? Let me find it here so I can remember correctly. Oh yes, the 3 quantities. So given a specific matrix X and vector phi, right, we want to compute 1 over p minus 1 sum k equals 1 to p xk squared. And then we also want to compute phi1 transpose c times phi1. And then we also want to compute 1 over p minus 1 sum x error squared, k equals 1 to p. Good. So first off, maybe I should say, how are we going to find, so these are you're taking a matrix, right, where the x's are in the columns, and then you're computing the norm squared of each of those, and then you're summing that together. So in other words, let's take a look at that first. So how am I going to do that? We'll come back to this, we'll save it. So suppose my matrix, it looks like this. Right, so in this case, we've got n by p. What you want to do, if this is your x, is if you take x and you square all the elements, this is MATLAB notation, by the way. If you square all the elements in x, then all you have to do is sum down the columns. And to do that in MATLAB, it's just sum. And so if you do that, what you end up with is a row, and this is x1 squared, and this is xp squared. Okay, so that's equal to this. And then what we wanted to do is sum these values together. And so therefore, if we want to sum the I columns squared k equals 1 to p, that's just sum x dot times x. Oops, it's all crooked there. Sorry about that. Okay, and I will let the Python people see how they might do that. Now remember that the sizes have to match, right? So if you've got an n by p matrix, this should be what size? 1 by n, or 1 by p, sorry. And then this, of course, is a scalar, right? So be careful with the sizes of things. Good. So now, that's how you do this one. Now this one is just the covariance matrix, right? So you can use the covariance command to do that. But be careful. What I want to say, what comes out of this is n by n or p by p. It should be n by n. So if the matrix X is like 3 by 4, right, then your covariance matrix should be 3 by 3. So we want to double check. So double check in your whatever code you're using that the covariance comes out as a 3 by 3 matrix. Okay, now in this case, I should say we don't have to worry about mean subtracting this, because the covariance will automatically, or the program will automatically mean subtract for the covariance. So in order to make sure that all of this works, I would say you should mean subtract this first. course, maybe we should just go ahead and just assume that everything's mean subtracted. Because then everything's going to work. You don't have to do it for some and then the others. Okay, so mean subtract your data first. Then finally down here, what is X error? Well, it's what's left over after you've projected your data to phi1. So for example, if I take x1, I'm going to have x1 is going to be the projection onto phi1, which is phi1 transpose x1 times phi1 plus x1 error. Do I have that one on top for the error? Yeah, so x1 error is going to be x1 minus that. Okay, and so what is this? How am I going to compute this? This is also the reconstruction using one basis vector, or one basis vector. And so you'll remember that the projection we had, if I have x, let's see, I need to make sure my sizes are right here. So if I want to project x onto the columns spanned by phi, that would be phi transpose times x, right? But then this has to be, let's make sure our stuff is right here. The stuff. Oop, I'm off the page. Are you shouting at me? Let's see. So am I right in terms of the size? If this is n by p, then this would be 1 by n, and that's good. And then this would be n by 1. And so the result is n by p, right? Yes. Good. And so what is the matrix that contains the error? The matrix that contains the error is going to be x error equals x minus phi transpose times x. Good. And so what is this? This is a matrix, right? I'm running out of space. Can I flip that? Oop, I'm running out of time too. So x error is going to have, your columns. X1 error. Oop, I messed those up again. Okay, you got it. Okay, and so then to compute this quantity, we can use our trick over here. That makes sense. I'm flipping pages around. Okay, I think that covers number 3. We'll come back for some more.